And 2 minutes of questions.
Okay, so am I audible? Okay, so my name is Ishant and I'm pursuing my PhD from Shivnadar University. And title of my presentation is Quantum Critical Spin Liquid State in Metallic Frustrated System at the Ambient Conditions. So, in contrast to insulating systems, a frustrated metallic system is less explored due to additional complexity introduced by itinerant charge degree of freedom. So, our motivation is to explore a frustrated metallic system, which is the ideal platform to explore novel quantum phases at the ambient conditions. So, we have explored in this periodic table 4f rare earth based metals, and so here you can see this 4f orbitals is very narrow band due to the overlapping between the 4f orbitals is very weak. So, on the top of that, this 4f orbitals, there is Coulomb interaction is very strong. So, as a result, this 4f bands become a highly localized. So, if we have metallic system, so there is a conduction electrons as well as 4f local moments are present. So, how they will interact? So, mainly two exchange interaction dominate in metals. So, first interaction is RKKY interactions, which is a indirect exchange interactions. So, in RKKY interactions, so this red one arrow shows the local moments, and this around there is surrounding is the conduction electrons. So, this is shown by this blue color. So, if the local moments are in the conduction electrons, so they will interrupt indirectly via RKKY interactions. So, this J is the exchange interactions between these local moments and the conduction electrons. So, here you can see this exchange interactions will like oscillate between this ferromagnetic or antiferromagnetic state. So, this exchange interaction depends on the R. R is the distance between these two local moments. So, this RKKY interaction tends to the long range magnetic, this leads to the long range magnetic order state. So, whereas the second interaction dominate is Kondo interaction. So, in Kondo interactions, so local moments are surrounded by cloud of conduction electrons which are oppositely polarized. So, now here effective mass of the electrons is greater than the bare mass of the electrons. So, this becomes a heavy fermions, and also so this leads to the non-magnetic many body singlet state. Okay, so by computing these interactions, we can achieve this quantum critical point. So, by this Donick phase diagram, so in Donick phase diagram, here you can see on the y scale there is a temperature, on the x axis there is an exchange interactions. Also, here you can see this Kondo interactions arises the exponential of the j, and this RKKY interaction this arises the square of the j. So, if you are at low j, so here you can see this magnetic ordered wins. So, if you are increasing this j, so this Kondo interaction, this quenching the movement, and we can reduce the magnetic ordering so that we can achieve this quantum critical point. So, also quantum fluctuation will be dominating around this quantum critical point, and physical quantities also diverge at this critical point. Also shows the power law behavior like susceptibility and heat capacity physical quantities. Also at this point, so this universal scaling behavior shows these quantities, these physical quantities. So, okay, so now the thing is we can also increase the quantum fluctuation by introducing this frustration. So, what is frustration? So, if we have triangular lattice and if we have Ising spins which can either up or down, so here you can see at the top corner of this triangular lattice there is up spin, and if we consider there is a antiferromagnetic interaction between the spins, so second spin is going down, and the third spins is confusing where to move, whether it is up or down. So, this is a highly frustrated, and it leads to the new states of matter like quantum spin liquids. So, in quantum spin liquids, so spins are highly correlated without any long range magnetic order state down to a very low temperature. So, now the thing is how we can achieve this quantum critical point in the real materials. So, here you can see if we have a system system has like a long range magnetic ordering state, so that we can suppress this magnetic ordering by this control or tuning parameter like hydrostatic pressure, chemical pressure as well as field. So, we can suppress this magnetic ordering, and we can reach here at the quantum critical point, and here you can see this quantum critical fluctuation will be dominating around this quantum critical point even at higher temperatures. So we can understand this phenomena by a known example, the cerium palladium aluminum, in which cerium is a magnetic moment, and also ceriums are arranged in the Kagome type structure, which is highly frustrated. And importantly, 2.7 Kelvin is the ordering temperature, so that we can suppress by this controller parameter, and which give rise to the exotic state, this quantum spin liquid behavior with the critical fluctuation, because around this quantum critical point there is a quantum critical fluctuation will be dominating. Okay, so now the thing is, at the ambient condition, can we achieve this quantum spin liquid state where we do not use any this external tuning parameter? So till now at the ambient condition only two metallic compounds, frustrated metallic compounds has been reported, and one of them cerium rhodium tin. So microscopic measurements has been revealed that there is a magnetic phase separation in the ground state. So now the question is, can such a state be realized in the clean system? And also here you can see both of the compounds are only the cerium based atoms which has the same Kagome type structure. So the next question, can we achieve this exotic state quantum spin liquid other than the Kagome lattice as well as the other than the cerium based atoms, especially at the ytterbium systems, which could be more exotic? So by looking at this, we have found ytterbium magnesium gallium 4 is the promising candidate, so in which ytterbium is a magnetic element and are arranged in the triangular lattice. And most importantly, here you can see this out of the plane interaction is 1.5 times higher than the nearest neighbor distance. So we have synthesized this material and performed this polycrystalline XRD. So here you can see this experimental peaks fitted with the theory peaks. So then we have measurement this magnetization, and here you can see down to a very low temperature, this is chi as a function of temperature, down to a very low temperature like 1.8 Kelvin, we didn't see any long range magnetic order state. And also we have plotted this 1 by chi as a function of temperature, and we have fitted this Curie Weiss law at the high temperature. So here you can see this Curie Weiss theta is minus 56 Kelvin. So this minus sign is, indicates that the antiferromagnetic correlation between the spins, and this magnitude of this Curie Weiss theta is very high, 56 Kelvin, and this indicates the system indicates that a high degree of frustration. Also we have estimated this mu effective, that is a 1.4 mu b is lesser than the YB3 plus state. So this states that the reduced effective movement indicates that the system is in the valence fluctuation region. To further confirm that, we have performed this XPS measurement. So here you can see at the room temperature, so this ytterbium valence is 2.86, less than the ytterbium 3 plus. So it is clear that the system is in the valence fluctuation region. Okay, so also we have plotted this chi as a function of temperature. So here you can see this shows the like power law behavior. So this indicates the system is in the quantum critical region, and also this chi we have performed this different fields. So if we increase the field, so this magnetization is suppressing. Okay, so to further check the scaling behavior, we have plotted here the first derivative of magnetization multiplied with critical exponent of field as a function of temperature and field. So here you can see from the lowest field to the highest field, they fall on the top of each other, and from the highest temperature to the lowest temperature, they shows the nice scaling behavior. So this indicates that the system in the quantum showing the quantum critical behavior. So to further check, we have performed this heat capacity behavior. So here you can see C by T as a function of temperature. So here you can see C by T showing as this power law behavior. So this is also consistent with the previous measurement, shows the like quantum critical behavior. Also we have C by T as a function of field. So also we have plotted this C by T with the this critical exponent of field as a function of temperature and field. Also this plot shows the nice scaling behavior. So it is consistent with the system is in the quantum critical fluctuations. Okay, so in the conclusion, we have found a ytterbium magnesium gallium 4 is a metallic frustrated compound in which ytterbium are arranged in the triangular lattice, and our experiment shows that there is a no long range magnetic ordering state down to a 350 millikelvin, And also Curie wise theta shows that system has a highly degree of frustration. So due to this frustration, this system shows this quantum critical spin liquid at the ambient conditions. So thank you.
Yeah, we can take one or two questions.
Nice talk. Just one short question. You have said that metallic spin liquid.
Yeah.
So have you performed resistivity measurement?
Yeah, resistivity measurement, but I didn't show here. So that is also proportional to the t power 1.
So you have tried to fit this magnetization with paramagnetic susceptibility formula?
Yeah, MH curve, I think.
MT.
MT, that I didn't try.
Okay. And just one question, that in your MT curve, I observed that it is at lower temperature, there is a Curie tail.
Yeah.
Right? So is it some what it signifies?
Like
Because like in any metallic system, it should be not too much like this behavior, Curie tail.
yeah, that could be like crystal electric field maybe.
So is the ytterbium uniformly mixed valent, or you have different ytterbiums having 3 plus and 2 plus?
So actually some not mixed valent, like it is behaving like mixed valent, like ytterbium 2 plus and 3 plus is not is not in the fully state in the ytterbium 3 plus and not in the ytterbium 2 plus. So there is ytterbium 2 sides, and like maybe some ytterbium is in the showing 2 plus and some showing 3 plus.
Okay, let's thank the speaker for a nice talk.
The Josephson diode effect in multi-channel Rashba nanowires, and in particular we'll be looking at the role played by the inter-subband coupling. So I'd like to begin with the idea of non-reciprocal transport. So non-reciprocal transport is not a foreign concept, at least in the context of semiconductor diodes. However, realizing this phenomenon in superconductors turns out to be not very trivial. And the reason is that because in superconductors, the current that flows is dissipationless, it doesn't have any resistance. Therefore, methods such as electron or hole doping do not work as in the case of semiconductors. So therefore, it took at least a few years until the recent few years where theoretical progress enables to observe this non-reciprocal transport effect in superconductors. So in superconductivity, the Josephson junctions serve as very versatile platforms to observe any kind of phenomenon. So a Josephson is basically a device which consists of two superconducting regions, SC1 and SC2 here, separated by a thin, let's say by a barrier, which can be a thin insulating region or a normal region. So the left and right superconductors can have order parameters psi1 and psi2, which have a different phase, phi1 and phi2. So the difference in the coherent phase of these superconducting states drives a current through the barrier even without any externally applied voltage. So that is called the Josephson effect. So in superconductors, this non-reciprocal transport is observed when the critical currents, that means the maximum currents, IC plus and IC minus, have different magnitudes. That means there is an asymmetry in the maximum current that flows in the forward direction and in the reverse direction. So that is a non-reciprocal behavior. So like I said before, in superconductors, realizing this non-reciprocal transport or diode effect is not easy. So we have to break certain kinds of symmetries. So the Josephson current that flows in the Josephson junction can be decomposed in general in terms of the Fourier components. So in time reversal symmetric systems, this Jn component coefficients is 0. So when this condition is obeyed, the current as a function of the phase difference phi obeys this kind of relation, right? So when this relation is obeyed, that means the positive and negative critical currents are of the same magnitude. They differ only by the sign. So that means we don't have an asymmetry in the maximum current that flows in the forward and reverse direction. Therefore, we don't have any Josephson diode effect. Therefore, this time reversal symmetry has to be broken so that this condition is no longer true. Okay. And another symmetry that needs to be broken is the inversion symmetry. So the inversion symmetry kind of does the same thing. It only reverses the direction of the flow of the current. So it has to be broken as well. So these two symmetries, the breaking of TRS and inversion symmetry are the essential but usually not sufficient conditions for JDE, but they are necessary. Now, in my talk, I will be discussing about the multi-channel rushbar nanowires, but before we come to that, I would like to discuss about the topological properties of the one-dimensional nanowire first. So we have here a 1D rushbar nanowire, which is placed on top of a 3D S-wave superconductor. So when it is placed on top of the S-wave superconductor, because of proximity effect, the rushbar nanowire also will become superconducting. So when an external magnetic field is applied along the transport direction x, right, Bx, so when the magnetic field is applied, what happens is it will lift the degeneracy at k point, k is equal to 0. So this is the dispersion of the rushbar nanowire. So when we apply magnetic field, it lifts the degeneracy here, and this region is known as the helical gap, right, because here the spin is tied to the momentum. Therefore, this region within this gap is called the helical regime. So in this regime, the system behaves as a 1D spinless chain, right. Therefore, it has topological properties. So if we study the topological phase diagram as a function of the chemical potential and the externally applied Zeeman field, we see that there is indeed a phase transition from a trivial phase into a topological phase. So the boundary here gives the critical transition point, which is given by this expression, right, root over delta square plus mu squared. So this is the case for the pure 1D system. So however, in realistic systems, you know, the assumption that this system is a pure 1D is not true, because there are finite size in the transverse direction as well. For example, let's say here the transport direction is along x, there will be finite size effects in the y and z direction, such as confinement effects. So these are the precise things that we are will be including in this study, and then we will see what are the new effects. So what we have is, we consider a cylindrical rushbar nanowire with confinement in the y and z direction. So we consider a harmonic kind of a confinement. So because of the translational invariance, because the momentum along y and z is a good quantum number, so we can separate the problem, and then it essentially reduces the y and z component reduces to a 2D harmonic oscillator problem. Therefore, we get this kind of discrete energy levels where the states depend on the two quantum numbers ny and nz, right. So so the different levels, energy levels, are determined by these two quantum numbers ny and nz. So in our study, we focus only at the two lowest energy levels. We consider the ground state and the first excited state. The first excited state is a degenerate state of two levels, right, indicated by this wave functions phi 10 and phi 01, because if you just put any one of these, either ny or nz, to be 1 and keep the other 0, they will be of the same energy. So what we do is, now we project the pure one-dimensional model on the space, on the basis of these two, on the basis of these lowest three energy states. So we basically what we do is, we find these matrix elements like this for each terms. So HR is basically the rushbar terms which couples the different transverse channels, right. So we find that only one of these excited state couples to the ground state. So we find that this matrix element is 0 and this one is finite. Okay, so that means this is irrelevant, it does nothing to change the physics. So we only consider this phi 10 energy level, and we find that the coupling between the ground state and this energy state is given by the strength of the spin orbit coupling alpha and W, which is the width of this nanowire or the diameter. So this quantity we call delta C, which is the coupling strength between the two bands, the interband coupling. Okay, so this is the normal state dispersion. So this is without any applied magnetic field, and here when we have a applied magnetic field, so we see that there are two energy bands, right, one for the ground state and one for the first excited state, and when we apply a magnetic field, it opens up a gap at this k0 point, it lifts up the degeneracy, we have the helical regime. So now that we have the system, so we'll be looking at how the topological phase diagram modifies in the presence of multiple channel. So first of all, we plot the low energy spectrum of the system. We see that for lower Zeeman field or Zeeman energy, the spectrum is gapped, but after a certain value, there's a critical transition point where we get zero energy states. So these zero energy states are the Majorana modes, which are localized at the edges of the nanowire like this. So however, once you keep on increasing the Zeeman energy, we find that the Majorana bound states or the zero modes are gone, right? And what that means is we have only a finite topological regime. But if there is no coupling between the bands, when the interband coupling is zero, we find that each of the band act independently, and there is an overlap of the Majorana in this regime. As we can see here, here we can get one pair of Majorana, and here we will get two pairs of Majorana, which is the overlap of these two subbands. However, when there is an interaction between the subbands, after certain points we don't get any more Majorana, and this is because up to here there is only an odd number of subbands that are occupied, but here there is an even number of subbands that are occupied. Therefore, the Majorana can hybridize, and then they will give rise to finite energy. They are no longer at zero energy. But if there is odd number of Majorana, then the even number can hybridize. The leftover will remain as a zero energy mode. Okay, so this is how the interband coupling modifies the topological phase diagram of the system. Now we look at the Josephson junction and we study the JDE. So here theta is the orientation of the magnetic field. So here we have, this is the geometry of the system. So we apply the magnetic field in the xy plane at some angle theta, and we can vary this angle theta theoretically. So we find, we look at the Josephson current as a function of the phase difference. When theta is 0, that means the Zeeman field is along a transport direction. We see that there is no asymmetry in the critical currents. The IC plus and IC minus are equal. Therefore, there is no JDE. So therefore, to have an asymmetry, to get Josephson diode effect, what we need is a finite component along the y direction as well, along the spin orbit direction.
Please conclude.
Okay, I'm coming to the end. So when we have a finite angle, we have an asymmetry in the critical currents, and therefore that means a finite JDE. So if we look at the efficiency to quantify the diode effect, we see that we plot the efficiency as a function of the magnetic field. So here is a trivial regime, there is no JDE, but in the topological regime, there is an enhancement in the efficiency because of the presence of this Majorana bound states. And in the independent channel, when they are not interacting, there is efficiency but much lower than the interacting channels. And we also see the main result is there's a difference here when the direction of the applied field is pi by 2, purely along the y direction, the spin orbit direction. We can get a finite Josephson diode effect in the interacting case. However, in the independent channel case, there is no Josephson diode efficiency. So that is a new effect that is introduced by the interband coupling. So to conclude my talk, we have found that the interband coupling basically modifies the topological phase diagram, and this spectral even odd effect is what determines this topological phase diagram depending on the number of subbands occupied, whether even or odd. And we see that the inter-subband coupling enhances the efficiency of the diode effect, and moreover it enables the diode effect with only single component, the transverse Zeeman field along the spin orbit directions. So these are the main findings of the program. So before ending, I'd like to acknowledge the group members who have benefited with my discussions, and also to my supervisor, Professor Sudeep Kumar Ghosh. Thank you.
One question, if there is any. Okay, let's thank the speaker once again. We will take the next speaker.
Hello everyone. So I am Subhanshu. I am a second year PhD student in science in ISC Bangalore. So I will begin my talk by thanking the organization for the wonderful opportunity. And my talk will be around our some initial result on spin orbit coupling signatures in bismuth thin films. So elemental bismuth emerges as a unique platform in condensed matter physics owing to its own exceptional structure and electronic properties. So talking about its structure, it's as a rhombohedral structure in which the number of bilayers stacks in uh, along the c-axis in ABC closed packing, and each atom in a lower bilayer connects with the three other atoms in the upper bilayer with covalent bond. So this structural property gives rise to different exotic phenomena, such as it is a very good semi-metal having very low carrier density and long mean free path, as well as as it is a heavy metal, it has strong topological surface state, and apart from that, a very strong property is that it has a transition from semi-metal to semiconductor that I will show in my growth also by doing some tuning in the growth parameters. We will see these properties. So in our work, generally we try to understand the type of SOC and try to answer the question that which type of SOC is dominating, and finally we just fill the bridge between the structural properties and electronic properties. So this growth is performed in molecular beam epitaxy system in which the substrate is silicon, and this growth has been made in 5e minus 10 millibar. So this growth pressure gives a very slow and controlled rate, which is very useful for the high quality thin film growth. And here I have shown the surface morphology of the film by SEM and AFM images, in which we can see with increase of thickness the granular size also increases. So it talks about that initially the bismuth atoms deposits on the silicon by 3D island, but with increase of thickness the lateral sizes increases and it enables the strain relaxation, which gives the continuous thin films. And we can see in the XRD also the signature peak for the bismuth along 003, 006 and 009 planes. And after that we move towards the electronic transport measurement, in which we see in the temperature dependent resistance measurement the semi-metallic behavior of the film, and around 100 Kelvin it behaves like metallic due to the grain boundary coherent scattering, and which can be correlated with the band structure of the bismuth, in which the conduction band at L point and the valence band at T point overlaps, and which we can see in the conventional Hall measurement, that is a temperature driven sign reversal of the Hall carriers. Generally in low temperature the electrons are dominating, in other case at high temperatures the holes are dominating. So apart from that, in the magnetic magnetoresistance study, we found that when it's subjected to out of plane magnetic field at high temperature it behaves as a B square, which is generally the orbital magnetoresistance behavior, but interestingly at low temperature it deviates from that behavior, and it giving rise to some features like weak anti-localization, in which generally the destructive interference, due to the destructive interference the carriers that are moving in a closed loop, the return probability to come back to the same path is got reduced, so the conductivity got enhanced, and it gives rise to some weak anti-localization type of behavior. So we fitted this data with the conventional HLN model, in which the target is to find the extracted parameters of alpha prime and alpha, which are generally the number of coherence channels and the coherent length, quantum coherent length. And this from this extraction we found that the alpha remains around 0.5, and this alpha also very greater than the thickness of the films, so which tells about the surface dominated properties of the film. And also in the when the film is subjected to the in-plane magnetic field, we seen something interesting, that is at low temperature it gives some positive magnetoresistance, but in the high temperature it's giving leading to the negative magnetoresistance, which talks about the bulk behavior of the film. And to investigate more, another type of experiment has been performed, that is the planar Hall effect. Generally in this case we rotated the film in XY plane subjected to the in-plane magnetic field. So here the generally the transverse voltage is not due to the Lorentz force, but it's due to the SOC induced anisotropy and it gives rise to some transverse voltage. So we did it for different films of different thickness and found that the amplitude is comparable for the different thickness, as well as it follows a sin 2 phi dependency. So which also tells about that this kind of behavior which arises from the surface or interface, not from the bulk. So concluding all of the results, we can conclude that a comprehensive study has been done on these films to evaluate its SOC nature, and the PHE, that is the planar Hall effect, also helps to distinguish between the surface and the bulk properties, and in future it will be helpful for the SOC induced devices as well as different bismuth heterostructures. And with this, I would like to acknowledge my whole group and my Professor Hall03 for her constant guidance and support. Thank you.